Hi all. When we began the study of physics, we began with the study of motion because I told you that motion is so fundamental. Everything around us is in continuous motion, and therefore, in physics, we try to understand the laws that govern motion. And we have come a long way, isn't it? There is motion all around us. I think when I move, there is motion. When a car moves, there's motion. When the fan rotates, there is motion. When you look outside, there's a lot of motion. Animals moving, there is motion. People moving, there is motion. The very earth is moving, there is motion. The very sun is moving, there is motion, isn't it? But if you were to now, take a step back and very carefully look at the motion that has taken place, you will realize that there are two types of motion that are taking place, right? Now just look at this marker, and I'm going to move this marker in a straight line, right? There is a motion that takes place like this. There is also another motion. If I take this marker and I start rotating it from its center, in the middle, suddenly you see a different type of motion taking place, right? So clearly there are two types of motions which are taking place in this universe, isn't it? So when I move, but how do you differentiate? The question is, how do you differentiate these two motions, isn't it? Or is it really different? And if you try to analyze this and you see, this marker moving in a straight line, all particles on this, now we know that this is a system of particles, this is made up of particles, all particles are moving the same distance in the same amount of time. Agreed? But now let's take the case where it is rotating in its center. Each particle is moving in a circle. Each of the, it's concentric circles that each particle is moving in. Clearly, the distance moved by each of the particles is not the same, isn't it? A particle which is more inside moves a circle with a smaller radius, and a particle at the far end of this marker moves in a circle with a larger radius in the same amount of time. That is, the distance they are moving is actually different, isn't it? But they're all moving in circles, right? And they're all moving in circles, and the center of all these circles would come on a fixed axis, right? Which is called the axis of rotation. All these circles, right? It is moving perfectly. Every particle is moving in a circle, and the center of all these circles will come on a straight line, which is called the axis of rotation. Now, this is what rotational motion. This is, in fact, the definition of rotational motion. That when a body is in motion, such that all the particles are moving in concentric circles, such that the center of all these circles lie on an axis, it is called rotational motion. Okay. And I want you to, probably, let's just say I have this sort of a motion. What is this? This will be a combination of rotation and translation. So you can see there is a translation motion taking place, and there is also a rotational motion taking place. Okay, so motion is a combination of translational and rotation. Okay, and in this particular video, we are going to clearly analyze just rotation. Right, we're going to stick to rotation, and we're going to analyze the motion, rotational motion. Right, that's our agenda. Now the question is, how do you analyze rotational motion? Okay, we have done the laws of kinematics, we have done equations, the laws of motion of Newton. Do these apply to rotational motion? Or do we need to come up with a new set of laws to analyze rotational motion? Well, here's the beauty of nature. Here's the most fascinating part about nature. The same laws of kinematics, the same laws of motion of Newton, conservation of momentum, all conservation of energy, mechanical energy, all these laws can be applied to rotational motion, in almost the same way, right? I'm going to say almost the same way because you will see that the quantities will change. In nature, there is something called as symmetry, right? And we apply symmetry, the idea of symmetry from translational to rotational motion. We try to see the synergy between the two, the connection, the symmetry between the two. Right? And you'll be amazed to see the symmetry between the two. That it can both be analyzed in the same way, except that in translation motion, every quantity in translational motion has a counterpart in rotational motion. And it's just so beautiful to see. It's so fascinating to see. And this is exactly what I'm going to show you in this video. We're going to analyze rotational motion. How do you analyze rotational motion is what we're going to look at, right? And to start with, I'm going to show you the parallel between translation and rotation. And that's the way we're going to analyze this whole thing. Okay. So when we looked at translational motion, I'm going to say this is translational and this is rotation. In translational motion, if you remember it, the first thing we said is fixing the position. To describe motion, you should fix the position of a body, isn't it? Right? And how did we do that? We drew a reference line, right? And we fixed a point O, which was the origin. That was the point of reference. And then we took a body here, which is, let's say, at x, at a distance x, right? There was the body here. And we said that the position of the body is at a distance x, let's say to the right, from the reference point O. That is the way we define position. Right? That's the first quantity you define in translational motion. Well, how do you do in rotation? Exactly, we are going to define position in rotational motion. Just that we're going to call it angular position, right? So I'm going to say in translational motion, we call position, we say x. Now, how do you do it in rotational motion? I'm going to draw something here for you. I want you to imagine it in a 3D dimension, okay? Saying that, look, there is an axis of rotation here, okay? And my marker is doing rotational motion. It is going around this way, right? And you can clearly see that it is in rotational motion. It is undergoing rotational motion. And this axis which goes into the board is the axis of rotation. Therefore, perfect rotational motion is taking place, right? What do? I fix a reference point. It's random, and it is, it's up to you where you want to fix it. Let's say I fix the a reference line here, right? And as it is going rotational motion at this point, right? My marker is at this point. I say it is at an angle theta from the reference line, right? At an angle theta which is measured in radians. This theta I define as the position of my marker, right? So let's say this is theta, and let's say it rotates more and it is another point, it is at this point. Then I say my angular displacement is theta, this angle, right? So the angular the angular position is given by the angle theta that the body has from any reference line that you're fixing. You can fix the reference line, but from then on, that becomes you can say that origin, the reference point, a reference line becomes, in this case, it's a reference line, it's not a point. In translation motion, it was a point, but here it's a reference line that you fix, and the body, when it moves at any position, can be defined with the angle it makes with that reference line. Got it? That is called, and I'm going to use angular position. Okay, so the first thing we define in rotational motion is angular position, and we use theta in radians to define the position. Now, once you define, let's come back to translation. Once you define position, now a body moves. When a body moves, changes its position, we say motion takes place, isn't it? And the way we measure this change in position first thing was displacement, isn't it? We said displacement is the next quantity we analyze, and we say displacement is x2 minus x1. That is, if a body is at a position x1, it moves to a position x2, the displacement is x2 minus x1 on a straight line. We saw that in translation motion, right? We saw it in straight line, this was the origin, x2, the final position minus the initial position was displacement. How do you look at it in rotation? Right? In rotation, I told you, here's the reference line, this is the axis of rotation. The body was first at theta 1, right? Initially it was the theta 1, now it rotates and moves to angle theta 2. What is the angular displacement? Because it's moved an angle. the angular displacement will be theta 2 minus theta 1, right? So angular, remember, the corresponding quantity of displacement is angular displacement. And angular displacement is theta 2 minus theta 1, right? What was the next quantity we looked at? The next quantity we looked at was velocity, right? And if you remember, velocity was the rate of change of displacement, that is d theta by dt. Here also in in rotational motion, the rate of change of theta is the angular velocity, right? So the counterpart of velocity is angular velocity. So I'm saying this is, let's not forget, it's angular velocity, and angular velocity is given by, velocity was v, and in translation motion it was dx by dt, right, was velocity, and angular velocity we give is omega, and it is equal to d theta by dt, right, omega. I've expressed omega. We've already seen it before in a circular motion. We already saw what omega was, but I'm just, this is a sort of revision where I'm telling you again what omega is. The third quantity we saw in translation motion was acceleration, right? And we know that acceleration was a, and it was equal to dv by dt, right? The rate of change of velocity was acceleration. Now, similarly, in when we look at rotation, the angular acceleration we call alpha, and this is equal to d omega by dt, the rate of change of angular velocity, right? So there is a position, the change in position was a displacement. So the angular position was theta, the displacement is theta 2 minus theta 1. The rate of change of displacement, that is d theta by dt, is angular velocity. The rate of change of angular velocity, that is d omega by dt, is angular acceleration, which is alpha. Hence, you're able to, the four main quantities of translation motion, you can see the counterpart, how we use them to define rotational motion. Okay. And now that we've defined rotational motion, the quantities, we're going to apply the equations of kinematics. We're going to apply them to rotational motion, right? And once again, I'm going to use symmetry to show it to appreciate it. We can always derive these equations, but I'm going to use symmetry to show you how the equations can be, right? Our first equation in translation motion was v is equal to u plus at. What do you think it's going to be in rotational motion? It's going to be, let's say omega is the final velocity and omega 0 is the initial velocity. This is the v and this is the u. Then final angular velocity is equal to initial angular velocity plus alpha into time. Time remains the same in both translational and rotation. The next equation we learned was S is equal to ut plus half at squared. We look at the rotational motion counterpart, theta, that is angular displacement, right, in radians, we know that, is equal to your initial angular velocity into t plus half angular acceleration t squared, right? And the final velocity, final equation we looked was v squared is equal to u squared plus 2as. And when we look at angular rotational motion, we know this can be equal to omega squared is equal to omega 0 squared plus 2 alpha theta. Right? The counterpart, final angular velocity, initial angular velocity, angular acceleration, and angular displacement. Hence, the laws of kinematics, the way we learned it, can be directly applied to rotational motion, just replacing the quantities of displacement, velocity, acceleration with angular displacement, angular velocity, and angular displacement. Okay, right. Thank you.